All right, so let's get right into it. Welcome back, everybody. Hope you all had a great weekend. Uh, Before we get going, I want to give just one quick note about the lecture question deadlines. I always recommend that you're able to finish the lecture question before the next lecture, but that's not always the case. I'll walk that back a little bit. As long as you're putting in an honest effort to complete the question and you have a general idea of what's going on, even if you don't get all the way to completion, that can be okay as long as you're able to get it shortly thereafter. And the reason I say that is because a lot of my lectures are designed to reinforce the content from the previous lecture. So you can sometimes, as long as you have a decent idea of what's going on with a lecture question, you can watch the next lecture to help you get to completion and really get those last things. Maybe you watch the next lecture and something clicks and says, "Oh man, that's what I was supposed to be doing." But as long as you're working on it, the reason I stress that so hard early on is because if you don't even look at the lecture question or attempt it at all, and then you try to watch the next lecture, then you're just screwed. Then you're starting to really fall behind, and that's not going to work for you. So with that said, let's get into this model of execution. And today, and really this whole week, these 3 lectures, we're going to start seeing where this learning objective gets its namesake of program execution. We're going to start peeling back some layers of what goes on in a program and look at how a program actually runs. I did make rhymes harder this semester, so be cautious taking that advice from P. It was easier last semester for sure. It might still be, but So we're going to see actually how a program runs. When you hit that green triangle in your IDE in IntelliJ, what's actually going on there? How does your program actually run? So that's what we want to start talking about. Last week we had to get some background before we could really talk about this stuff, namely classes. So your lecture question today, just like Friday's was kind of a lead-in into rhyming dictionary homework, this one is a lead-in into physics engine. So this is, especially if you're doing that assignment, this is going to get your feet wet a little bit, get a little bit of an idea of what the topic is for physics engine. And if you're not doing the assignment, doing these 2 lecture questions can at least help you decide which one to do. So for this one, in a class named physics, create physics vector. If you already cloned the repo for the physics homework, you already have a physics vector class created for you in the physics package. And you can start with that. If you want to start with that as your starting point, that's fine. If you want to create it just for this lecture question, maybe you're doing rhyming dictionary and you're settled on that, that's fine too. But at any rate, you have to have all these features and have them tested, starting with a constructor that takes 3 variables. They have to be var of type double named xyz. So this is a point in a 3D space, or rather a vector in a 3D space, defined by its x, y, and z coordinates. 2 methods, one multiply by constant that takes a double and returns unit. Both of these methods that you're writing are going to return unit. This one takes a double and multiplies x, y, and z by that input, whatever double was input. So if I have a vector that I said new physics vector of 2, 0, negative 1.5 for its x, y, and z, and I call multiply by constant of 2 on it, it's going to be, its x, y, and z are going to be 4, 0, negative 3 respectively after that call. Now notice that this doesn't return anything, but it does change the state of the object. So this is very similar to what we did, what we saw on Friday's lecture. This is an extension of working with classes. So even though this doesn't return anything, it is going to change the state of the object on which it was called. Oh, Doggo wants to say hi. Hey, pup, say hi. Look at the camera right here, Doggo. This is Kobe. He was crying. He came up here wanting to see me. So even though it returns unit, it is going to change the state. So it's going to change the values stored in these 3 variables. You're just going to sit on my lap, dog? You're a little too big for this. It's going to change the values in those 3 variables. So we don't always have to return anything. Sometimes we call methods just for their side effects, and this is one of those cases. We're going to call this method just for the side effects of that method call, which is changing the x, y, and z. Same thing with the next method, add vector. This is going to take another physics vector as a value, and it's going to add the x, y, and z of that physics vector to the physics vector that this method was called on. So this method is only going to take one physics vector as its argument, or as its parameter, but it's going to have access to two physics vectors, since methods inside an object always have access to the calling object's state. So we can always use this.xyz to access the xyz of the physics vector on which this method was called. So if I have vector.addVector, I have access to that vector that called it, and also access to the vector that it was called with as an argument. So, all right, Doc, you gotta get off my lap. So we have access to both those vectors, and we're going to add the vectors, add the values of the argument vector or the parameter vector to the calling vector. So this is a little tricky. This is where a lot of students get tripped up, and we start using the keyword this. But that's going to be a little tricky until you see what's going on, and I really want to emphasize that keyword this is a reference to the calling object through this lecture question. And then the testing, it's just one sentence here, but it's a very unassuming sentence, but this is a tricky one. How do we test this? How do we actually create new vectors, call these methods, and use these methods? This is probably the more important part of the lecture question as well. How do we actually use these vectors and these methods in this constructor after we write the code? So that's the lecture question. That's what we want to get to today. With Friday's content, you could be able to complete that lecture question right now. This is one of those instances where today's lecture isn't necessary to complete the lecture question, but it should help you at least in some regard, and it certainly will help you for Wednesday's lecture question, but it doesn't quite fully prepare you for Wednesday, so I couldn't have Wednesdays on today. But anyway, but you should be able to do that from Friday's content. P got timed out. I don't know why. I'll have to ask Lana after lecture. So kind of a quick side note. This is something important, but I don't really know what lecture to put it in, to be honest. So I threw it in this one once we start talking about executing programs. Is interpretation versus compilation. These are two different ways that programs are run. And I just want to talk about the difference for a little bit. Interpretation, this means that the code is read and executed one statement at a time. The interpreter will take your source code, the code that you write, and run through your program starting at the first line of main and just run each line, each statement that you've written, and execute one after another, and go through the program like that. This is as opposed to compilation, where the entire program is read all at once, translated to another language, and then that language is interpreted by an interpreter. That'll be an interpreted language, and run one line at a time as it executes. But with compilation, your source code is never actually ran directly, but your source code is translated into another language first, and then that other language, your program in that other language is going to run. So Python and JavaScript that you saw in 115, both interpreted languages. There's a little bit of nuance to that point, but for all intents and purposes, they're interpreted languages where they're run one line at a time. So in these, what you probably felt last semester is runtime errors are actually pretty common with this, as opposed to compilation errors, which we see in Scala, and I'll talk about next slide. So the program runs a or a Python program or a JavaScript program will always, I'll say almost always, I'll hedge it a little bit, but they'll practically always run, but they might crash after they run. That's because they're interpreted. So if we have this program in Python, we're going to run this, and this is some of the syntax for a class and main method in Python. We have this main method. We create a new object of runtime error example, calls its constructor. Syntax different, but the same concept that we've been talking about. Call its method add to state with the value 10. Print adding to state, just to give us an indicator of what's going on. Self.add, we're going to go to that state variable and add 10 to it. and then print out the state of the object, which will be 15. This program runs without errors. This is a great Python program that works and does that thing. As opposed to this program, all I did was change this little bit here. We get the same behavior. The constructor runs, add to state is called, but now with 10 as a string in quotes, we have a different type, and there's nothing to enforce the types here. We don't have any types of our parameters, no types to anything in Python. We have don't have strong typing for this. So now we get to this line. The code is executed one line at a time. Print adding to state. The program runs, gets to that print statement, prints it to the screen. We can see adding to state printed to the screen. The program ran up until that point. And then when we get to self.state plus equals to add, we're going to get a type error. Python's going to say, yo, you gave me an int and a string and asked me to add them together. I don't know what's going on. And the program just crashes and won't execute anymore. So that's a runtime error. The program was running, and then at runtime, it crashed. P, why are you asking about exams? You know, like, we talked about this on day one. There's a syllabus. So compare that to compilation, which Scala, of course, the one we're using, but also Java, C, C++, some other languages you've at least heard of or may have worked with. These are all compiled languages, which means we're converting our source code into another language that is then going to be interpreted. So in this, compiler errors are common, as opposed to runtime errors being common. We can still get runtime errors. We still will throughout the semester. But compiler errors are more common than runtime errors, or rather, they exist, whereas they didn't in JavaScript and Python. So before you can run your code, the compiler is going to check, and this all happens once you click that green button. All the compilation and then interpretation of the second language all happens all rolled into one. So your compiler errors might feel like runtime errors. But your entire code is going to be looked over. All the syntax is checked. All the types are checked. So if you're returning one type but storing that return in a value of a different variable, a variable of a different type, then it's going to give you an error, and it's not going to be able to convert your code into that other language. It won't be able to compile. You'll get a compile error, and then you just can't run the program at all. So you can't ever convert it to the other language, so a course can never run, and your code doesn't run. So same example from the previous slide, just in Scala, is we get this code that runs fine. We have the 10, the 5, everything's great, prints 15, adding to state 15 to the screen. But when we have this error here, the code never runs at all. This is going to be a compiler error because add to state takes an int. We gave it a string. The compiler says, no way, I'm not even going to touch this code. I'm not running this. I'm not doing anything with it because there's an error. There's a compiler error here. So this, when we click the green button in our IDE, adding to state is never printed to the screen because this program never was able to run because the types, the strong typing kicked in. The compiler said, this just doesn't work. This isn't actually a program. And strictly speaking, this is not a Scala program because it doesn't follow the proper syntax. It's might as well just be any characters strung together. It's not a Scala program, strictly speaking. So the language that Scala is compiled into is Java bytecode. This runs on the JVM, Java Virtual Machine, and if you've ever seen this pop up, any of these pop-ups that says update your Java, that's the Java Virtual Machine, which runs Java bytecode. So to run Java bytecode, we use the Java Virtual Machine. Scala is compiled into Java bytecode, runs on the Java Virtual Machine, which is installed on like pretty much everything. Everything, most machines, any laptop or anything, or desktop is going to run Java. Many phones, Android phones at least, some toasters, and Java's everywhere. But yeah, we do have to deal with Oracle with that. Oracle's controls this to an extent. Let's not get into that though. But any program, any computer that runs Java can run your Scala programs. And also, Java also compiles down to Java bytecode, of course. That's where its name comes from. So we can actually mix Java and Scala code in the same program. Since they're both compiled down to Java bytecode, by the time they're actually executed and run in the interpreter, the Java virtual machine, they look identical. The JVM can't tell the difference between Java code, Java bytecode that was compiled from Java and Java bytecode that was compiled from Scala. It's the same thing at that point. So we can mix Scala and Java as much as we want. We can mix them in the same program. And in fact, we will do that throughout the class. We already saw that the math class, I went into that in, I think, Friday's lecture. I went into that and I said, oh, Scala's math, I forgot, is actually Java's math class. Scala actually uses Java's math class, and a lot of the Scala standard library just borrows from Java. It's all Java code. And we'll use some Java libraries, specifically JavaFX later in the semester, which you ran in the first lab, but we will see that more in depth pretty late in the semester. Yeah, their legal team's 9 times the size of their dev team. Yeah, that's the problem. I feel like they stopped really developing. They're just, it's just lawsuits. It's a lawsuit company now, which is unfortunate. So every, and this is somewhat a side note, we're going to spend the rest of this lecture and next lecture, most of it anyway, talking about what this means. But references, every class you create will be passed by reference. So if you pass a class into a method, then you actually don't pass that a copy of that class. You pass that, or object, sorry. You'll pass that object itself. That should say every object you create will be passed by reference. Every object. So all these data structures, list maps, arrays that we use, all the built-in classes, any class that you write, objects of that type are always passed by reference. So any changes made to that object by the method will be reflected outside of that method as well. And we'll see why that's the case as well. So if we have this example building off of the code from last lecture, we create a new item and we call a method called increase price, which takes an item and increases its price state variable. That price change will be reflected outside of that method call as well. So when we say increase price of cereal, we're actually passing this object, actually a reference to this object, to the method. So even though this variable is called item, and we access item.price, this is actually the same object that's stored in the variable cereal. So when we call this method, cereal's price will be increased by a quarter in this case. And if we have an assignment, cereal2 is a new variable of type item equals cereal. This is only assigning the reference. So both of these variables refer to the same object, just like item of type item equals cereal, that implicit assignment from parameter to argument. That assignment was by reference. Assignments like this are also by reference. So cereal2 and cereal refer to the same item, the same object. If we call increase price of cereal2, that's the same reference that's referred to by this variable at this point in time in the program. So we get that plus a quarter again. So twice this cereal object was increased by a quarter. So when we print out the price, that price of cereal is now $3.50 because its price was increased twice. Even though only one time was the variable cereal actually given to increase price, its reference was still given to increase price through cereal2. So there's so one way to look at this, if you want to look at it this way, and one way to kind of see this, is only one item was ever created. Only one object of type item was ever created in this whole program. So anytime increase price was called, it had to have been working on the same item, because we only used new once. We only created one object. So every time increase price is called, it's always that same object. When we call this method, we don't make a copy of the object and send a copy like we do with ints and like we do with doubles, etc. With what we Well, the next slide will cover that. We only create one object, and every time increased price was called, it had to have been working on that same object, because where does another object come from? They're not created unless we explicitly say create a new object. It's similar to pointers. Pointers are a little bit different, but if you want to think of that for now, at least until you get into 220, you should be okay with that. Once you get into the actual difference between pointers and references. And so one warning on this, if you're starting the physics engine homework, there's a method that's going to ask you to remember the previous location of an object. So previous location and location have to be stored separately. And if you're remembering the previous location by just assigning the current location, well, now when you update the current location, previous location is also updated because you just did assignment by reference. So whenever you change one of these, the other will change also, which defeats the purpose of remembering the previous location as the current location is updating. So one caution with that, that's one big trap that you could fall into with the physics engine homework or any code that's using objects. Just understanding that they're being passed by reference is going to be something that you have to look for. Okay. So that's some background. The references are going to make more sense as we talk about memory. In interpretation compilation, it's something that just something about Scala. You have this new language. You might be noticing a lot of different behaviors. Some of that is coming from the fact that it's a compiled language. 220 before 116. Toldfish. No, who said that? Yeah, it doesn't matter. Yeah, to be honest, yeah, P said that. I see you got transfer credit for 220 but not 116. So let's talk about memory. This is RAM. If you've built a computer or if you've torn one apart at any point, you've probably seen these, or if you ever upgraded your RAM, you've seen these RAM sticks, and you know, at the very least, you probably know that these are important for the speed of your machine, even if you don't understand quite why. We're going to talk about that a little bit today. So RAM is like a giant array of memory for your computer, and all of your values for all of your running programs are stored here. So if you don't have a lot of RAM in your machine and you're trying to run like 10 programs at once, you're going to notice a big slowdown because all those programs are trying to take up a chunk of your RAM. And once you run out of RAM, things get really, really slow. Once you fill up this entire array with program data, things get slow. Because reading from disk is a lot slower than reading from RAM. Reading from RAM is very fast. It also makes RAM more expensive dollar-wise. RAM is expensive to buy, but it's so much faster that it's worth it, which is why we don't have just a terabyte of RAM in our machines. But RAM is very fast to read and write from, so when your programs are running and they're constantly changing data and updating data structures and everything, we want that to be fast. So we put that in RAM. If we ever have to go to disk for information, that's a very slow process. For those of you doing rhyming dictionary, you have a giant file that you have to read from disk. And if you're sloppy with your code, you could end up reading this file over 100,000 times from disk, and you're going to time out on Autolab. You're not going to have enough time to run that whole program because reading from disk is very, very slow. We don't want to do that. Even with an SSD, if you have a solid-state hard drive, it's still prohibitively slow for programs. So you want to use RAM. You need to download more RAM. And once you run out of RAM, machines will do what's called paging, which uses your hard drive as RAM. So it uses a chunk of your hard drive space as extra RAM. But since it has to read and write from disk over and over again, that's where you get that real big slowdown once you exceed your RAM sticks. So what does this mean in the context of us writing programs? Is once our program starts executing, that we're going to ask the operating system, or rather the JVM is going to ask the operating system that we're running for a chunk of memory. It's going to say, hey, can I have memory? I got a program to run. I'm going to need some memory to execute this. Operating system, in most cases, is going to say, cool, unless something's going horribly wrong. It's going to say, cool, here's the memory that you asked for, and you have to stay within these bounds. Here's a chunk of memory and before and after that, that memory might be used by another program. It might just be reserved by the OS or whatever it's being used for. But at any rate, it's not allocated for the run of your program, so we cannot use it. So we have a chunk of memory that we're allowed to use, and we're going to use that for our program. There's some structure to how that data is used. There's some, if you read the reading for today, there's some things at the bottom for program data, store some meta information about the program that's running. The exact details of that portion of the memory that's allocated isn't pertinent to 116, but it will start becoming more important as you progress through your career. So we won't worry about that program data here, but we will worry about our program data, our memory that we're using, and kind of the command line arguments. I'll at least mention those and leave them on the screen, but we won't really deal with command line arguments in this class either. But we're worried about all this, our program memory that we talk about. I mean, what type of RAM I have isn't really relevant to the lecture. You can ask after, but it's not really important to know right now for this lecture. Yeah, it's all temp storage. RAM is all temporary. On Friday, I think I even went through my specs. Where were you? I'm not going to keep doing the same things over and over, especially when they're not related to the course. I'm fine getting sidetracked sometimes, but not multiple times on the same thing. Data stored. So our program data is going to be stored on the memory stack. We'll talk about the memory heap also a little bit later, but the memory stack is going to be where all of our variables and values are stored. At least for now. I'll introduce the heap later, but for now, let's just think of a simplified view where all the variables and values of our program are stored, and this follows a last in, first out data structure type. So only the data on the top of the stack can be removed from the stack, and data can only be added to the top of the stack, or the bottom. We'll kind of draw it upside down, as you'll see. So this is the only thing we can do. We can only modify the top of the stack in terms of allocating more memory for more variables. Furthermore, whenever a method is called, we're going to create what's called a new stack frame, and whatever stack frame is currently executing is going to be kind of like a confined environment for our program to run. This happens whenever we call a method or a function. We're going to create a new stack frame, and we're going to remain in that stack frame and only be able to be confined in that stack frame. We'll be confined to that stack frame until that method or function returns a value. Then we destroy that stack frame and go back to whatever stack frame called that method. Similar to stack frame are code blocks. Whenever a code block begins, so any conditional loops or anything, whenever we start a new code block, we also segment our execution. The interpreter is going to segment that execution after compilation and everything, and only variables, but not to the extent of a stack frame. In a code block, we can still access variables in the same stack frame that are outside of that code block. So inside an if statement, you can still access variables that were created outside of that if statement. But there are some differences between those variables in and outside of the currently executing code block. So for example, we can have variables and values with the same name both in and outside of the code block, but in a single block we cannot have variables or values with the same name. So if we have a variable with the same name in and outside a code block, the interpreter will first look inside that block for a variable with that name. If it doesn't find one, it'll continue its search outside of that block, but always within the same stack frame. And as soon as we reach the end of a code block, this all makes so much sense. It shouldn't yet. I have examples for the rest of the lecture. Once you hit the end of a code block, any variables or values that were declared within it will be destroyed. Some of that should be familiar from 115, the idea of variable scoping you've ran into before, but let's make this a little more concrete and give it some pictures. So, what does all of that mean? Let's talk about the memory stack, and I want to go through the execution of a program, this program right here, and I will keep this program. It's almost JavaScript code. It probably would actually run as intended as JavaScript, just coincidentally. But this example is meant to be language agnostic, so I can talk about the just the execution and focus on the memory and the stack memory without thinking about any specific language. So we have a program here with a function. It's going to compute the factorial of its input. It's going to start at 1, iterate over all the values from 1 to its input. Could actually start at 2 if I wanted. Be the same result. And just keep multiplying all the values together. So this should loop from 1 to 5 in this case, and multiply 1 times 2 times 3 times 4 times 5, and then return that result, which should be 120 if I'm remembering right. So call that, store it in a variable n, and then just print it to the screen. So we're just printing 5 factorial to the screen. So let's run through this and give the stack a picture. We're going to go to that picture. We're going to stay in the confines of our program. We're going to start with the command line arguments stored on the stack, which again we won't work with in this class, but they'll be the first thing on the stack. And then any new variables that we add are going to go in the next open spot in the stack memory. So, when we get to the first variable declaration, we're going to create a variable named I and assign it the value 5 and add that to the stack. So we need to have some space in memory. In this stack memory, we're going to add that value, write it down, and keep track of that value by writing it on the stack, pushing it onto the stack, as it were. Is this Scala or C++? I literally just said that. It's no specific language. It's language agnostic. But it happens to be close to JavaScript, just coincidentally. So we're going to add that to the stack, give it the value 5, and remember that value. Then the next thing we do, we get to this assignment operator. We can't declare n or assign it to anything until we resolve the right side of the assignment. So the right side value is a method or a function call in this case. So we have to call this function and have it resolve to a value before we can declare n and assign it to n. So we actually don't add n yet to the stack yet until the method return or the function returns. I'm going to keep saying method on accident. Until the function returns, that's when we're going to be able to declare n, add it to the stack, and then move on with our program. So we hit a function call. Jeez, I should have just wrote it in Scala because I'm going to say method anyway. We're going to get to this function call. So when we get to a function call, we're going to add a new stack frame to the stack, and we're going to mark just right here visually that we're starting a new stack frame, which means we're starting a separate form of a separate area of execution where we can no longer access anything outside of this frame. So once we enter this function call, we no longer have access to this variable I from the main method, from the main stack frame. We don't have access to that variable I anymore. We only have access to the variables inside this function, which for now are just, once we enter it, are just the parameters. So we take the parameter n, any parameters that we have, we're going to declare those as variables, and we're going to assign them the arguments of the function call. In this case, I, which resolves to 5 because that's the value it's storing. So we, inside the stack frame, create a variable named n, assign it the value 5, and move on to the next line. We're going to hit this next line, result equals 1, add that to the next available spot in the stack, name result, value 1, name result, value 1, add that to the stack inside the stack frame so we can remember that value. Are you able to pass this class without knowing any coding prior? Maybe, but probably not. This class is intended to be a second semester in programming, or in computer science rather. So without 115 background, that'd be really tough to do. Yeah, 115 is a prereq for the course. 115 you should be able to pass without any prior experience. Not so in this class. Yeah, and I think there's a lot of trolls in chat. But anyway, so create result, add that to the stack, which sucks. I want to interact with chat. Hopefully a couple of trolls don't ruin it. So let's add that to the stack and then enter this loop. We enter the loop block. This loop, if you haven't seen a loop, a for loop written like this is a three statement loop where we have an initializer, which is going to be run once. As soon as we reach the loop, this is called. So we'll create a variable named I of value 1 and add that to the stack inside the block for that loop. And we have a conditional to check. Every time we get to the loop or get to the end of the loop, we're going to check this conditional. If it's true, execute the loop. And whenever we get to the end of the loop and before we check the conditional, we're going to run the third statement, which here is incrementing I. So we're iterating through from I to N and executing this code for each value. So we're adding I to the stack inside the loop block, hitting result times equals I. So we look for result inside the loop, or actually first we look for I. We look for I inside the loop block. We find it. It has value 1. So the right-hand side resolves to 1. And then we look for result inside the loop block. We actually don't find a variable named result. So we're going to expand our search to outside of that block, to the next level of execution. Outside of this block, but still staying within the stack frame. We do find a result. Its value is 1. So we have 1 times 1, and then reassign that back to result. Still just 1, so nothing really changes. The next iteration of the loop, we hit the end of the loop, increment I. So I is now 2. We found I inside the loop block, so we'll take that variable and increment it. And check the condition, 2 less than or equal to 5. 5 we don't n we don't find inside the block, but we find inside the frame. 2 is less than or equal to 5. So we're going to execute the loop again. Result, we do find, which is 1, and I is 2 in this case. 1 times 2 is 2, so reassign result to 2. So now this line updated result outside of the loop block and updated its value to 2. And then we do the same thing for every execution of the loop. And once we multiply, we go through the whole loop. I won't unfold the whole loop. That's a 115 topic. We're going to end up with a result of 120. Now notice that result was declared outside of the loop block. So when it was created in the stack frame, but not in the loop block. So when we get to the end of this loop, we're going to destroy every variable that was created as part of that loop, including its variable that we used for iteration. All of that gets destroyed. So if we did declare result inside the loop, we get to the end of the loop, result would be destroyed. It would be erased from the stack completely. We hit the end of a block, everything in that block is gone. We destroy that memory. It's all gone. So, and this is a common 115 mistake, especially for conditionals. You say if some condition, declare a variable X, assign it some value, do some math, and then exit the conditional and then return X. That's always going to give you an error because X doesn't exist because it was destroyed as soon as you hit the end of that block. Whenever you hit a closing brace in languages that use braces, you're always ending a block of code, or in some cases a whole stack frame, but still defined as a block of code. You're destroying things on the stack. Anything declared in that block is gone. It's destroyed. So now once we get to the next line, return result, we do have a result. We do have a result inside the stack frame. We find it. It has value 120. So our return value of this stack frame is going to be 120. We're returning 120. So this whole stack frame is now destroyed because we hit the end of its block. The whole stack frame is destroyed anything declared inside of that function is destroyed. So result I was already gone, n, those are destroyed once we hit a return statement, and then that block resolves to that value that was returned. To reserve more memory for your program, there are JVM parameters that you can give, but the default stack size is pretty large that you're not going to exceed it unless you do something silly like an infinite recursion, which we'll talk about on Wednesday actually. But you typically have enough memory to do what you need to do. But there are ways that if you do run into that, you can give the JVM some extra parameters to say, hey JVM, when you start this program, can you ask for more than the default memory for my stack? So that function returns 120. Now that we have a return value, we're going to go back to where we were in the main stack frame. So we'll go back to this one, back to this line that we were waiting on. We were sitting here waiting for compute factorial to return, which created a frame, did all this stuff up here, and now all that resulted in just returning 120. From the main method's perspective, we don't care about anything that happened with that other stack frame. We just care that this resolves to 120. And now we can declare n, and assign it that value 120, add that to the stack, and then we just print it to the screen for this program. Very exciting program, I know. And at this point, we don't have access to any of those variables that we created. N, result, I, none of those exist anymore. We do have the I from the main method, which is a different I from the function, the I in the function. That I still exists because it was outside that stack frame. But the I from inside the for loop, which was inside the stack frame, that's been destroyed a long time ago. And then we hit the end block for our main method, free up all the memory of the stack, give it back to the OS, tell the operating system, hey, we're done with all that memory we asked for, you can have it back. And there's just no memory of our program remaining. It's all gone, nobody remembers that it ever existed, and until we run that program again. All right, so stack memory, only what we call primitive types are stored in the stack, and I'm borrowing that from Java, the term primitive, are stored in the stack. For our purposes, that's double, float, int, long, short, char, byte, boolean. I don't believe I'll introduce any of them other than these, and I don't even know if I miss it. I have byte. I might not even be missing any. That might be a comprehensive list. These are stored in stack memory. These correspond to Java primitives. There are no primitives in Scala, but since Scala is compiled down to Java bytecode, when these classes and objects of these types are used in Scala, once they're compiled, they are converted to the primitive types in Java bytecode. So we actually do get the effect of primitives in terms of stack and heap memory, but we use them as classes when we write our source code. But that source code, remember, is never executed. It's always executed as Java bytecode after compilation. So we're still thinking of these as primitives, even though they are classes and objects of these types. Everything else is stored in heap memory. Everything else. So what's heap memory should be your question. And we are using a little bit of a simplified view of stack and heap. With modern architectures, modern compilers and everything, you never know where things are actually being stored because they're going to have so many little optimizations written in there. But for our purposes, stack, everything else heap. That'll be important throughout the semester, by the way. Stack, heap, everything else heap. So, the stack is very structured. Let's start talking about the heap and seeing why we even need the heap to begin with. So let's look at this program. I'm going to create a list, which is not one of those things that we called primitives on the previous slide. And this is Scala code this time. A list with the values 2 and 3, put a few things on the stack, and then modify the list, update that reference. So we know list is going on the heap. I spoiled that one already, but let's see why and what could happen if it wasn't on the heap. So let's try putting this list on the stack. So when we put this list on the stack, we actually have to allocate room for 2 integers. So we have our command line arguments and then this list, which has 2 values. It's going to take up 2 spaces, and I'm being kind of liberal about how the space is represented. It's not always just one chunk. We would actually go down to, these are ints, so these are 32 bits. My doubles are going to be 64 bits, but we're not going to get into that level of detail at this point. In this course, I should say. We're never going to do that in this course. And then we get to the next 2 values. We're going to put those on the stack, x with 5, y of 12. Throw those on the stack in the next available slot. And then we get to an issue right here. We have to update the list. We're going to create a new list with 1 prepended to 2 and 3 and reassign it to this variable list. But how do we do that? How do we do that with the stack? So let's look at a few bad options. One option would be just expand the list and put the 3rd value right after that 2nd value. The problem is x is already there. X already has that part of the stack. And really we can't do this because we can only add and remove at the top of the stack. We could remove y, we can add after y. Those are the only 2 things we can do to modify what's allocated on the stack. We can change values anywhere on the stack within the stack frame that we're executing on, but we can't allocate more space in the middle of a stack. So we can't really do this. One thing we could do is pop all the values off of the stack up until we get the list, then add 3, the next element, to the list, and then push all those elements back onto the stack to be able to get that dynamic allocation of memory. Problem is, if we just push all those values down by popping them all and then pushing them all, it's just too slow. We don't want to do that. Option 2, well, why don't we move the list down to the top of the stack and add all its values here. Then if we leave the other list here, then we have 2 variables in the same code block with the same name. So we can't do that. So why don't we erase that? But for one, this is slow to copy the entire list. What if this list were 1 million elements and we just copied the whole thing over again? And it also leaves gaps in the stack, which are problematic for a lot of reasons. The stack can get really looking like Swiss cheese after a while, which is going to waste a lot of memory and increase your chances of overflowing the stack, which are all bad things. We don't want to do that either. So our 3rd option and our good option, this is what actually happens, is when we create a new list, we're not putting it on the stack. We are putting it in the heap. So the heap is more dynamic memory, where whenever we need heap space, so whenever we create a new object, we're going back to the OS or the JVM, if the JVM manages this a bit. We're going back to the JVM and saying, yo, I know you gave me that stack space, that was cool and all, but I need more memory. Give me some more memory. I don't care where it is. I don't care anything about it. Just give me this much memory somewhere on that RAM stick. And in our cases, give me enough memory to store 2 ints. And we're going to get enough memory to store 2 ints, and we're going to put it somewhere. We don't really care where these values end up, but we're going to get the location of that memory. And that's what we store in the variable list. In any variable of any object type that's not one of those primitive types. We're only going to store the location in heap space of that value that we created. This new list we created, tell me where it is in the heap. I'll modify the heap to get the memory, the data that I want there, the values that I want, and then just give me the location of it, which we call a reference, and store that reference in the variable. Now we go on with our program. We add x and y to the list. And when we reassign list, we're going to allocate more memory in heap space. We're going to get this value 1, which points to 2, which points to 3. We'll talk about that in much depth when we get to data structures and linked lists. And reassign list to the location of the value 1 in heap space. So now instead of referring to 2, it's going to refer to 1. And now the heap is going to control how this list is going to change and how new lists are created and what's going on with that kind of more dynamic memory. This heap space can change, things can move around, very dynamic. It doesn't have this very strict structure of you can only remove the top element and you can only add after that top element. It doesn't have that restriction. It's pretty much do what we want over in heap space. Much more dynamic. It's sometimes just called dynamic memory in Stack. The heap is very dynamic. Let me just very quickly go through this. Maybe I'll go through it again. So let's do another again on Wednesday, or I'll just do my more in-depth examples there. So let's do another language agnostic examples. Yeah, you can stay. I have another class in 20 minutes, but I always stay for that 20 minutes in chat. So let's create this class. We actually create it in memory in the heap space, which I'll start referencing like this. We're going to say at 387, which is just some made up number that I chose. That's the location in RAM where this is stored. And then all we store in data, the variable, is that location in heap space. And then the location in heap space actually stores the state variables of this object that we created. When we call a method that takes an object, we're only passing that address. We're passing at 387. That's the only thing that gets passed to the function here. And then the function in this case is going to look, okay, at 387. Let me go there. And then I need to, at 387, access its state var and add 1 to it. It makes that change. It returns the stack frame's gone. But in the main method, when it's, I forgot my at sign there. But when it needs to print data.stateVar, even though these are different variables, they refer to the same object. So data is data at 387.stateVar. It's going to go to heap space at 387, and it's going to find that stateVar was increased by 1. That change was reflected because it was made in heap space, because this was passed by reference. It just passed the location in memory of that object, not the object itself, not a copy of that object. It just passed the location in memory where that object lives. So then the function followed that memory address, went to that spot in memory on the RAM stick, made a change, and then that whole stack frame was destroyed, but that change persists. That change actually is reflected in the main method, because the main method is going to that same spot in heap space. And heap space is not destroyed when a stack frame is destroyed or a code block is destroyed. That variable storing the reference was destroyed. That variable was destroyed, but heap space remains. And I still have a reference to that same spot in heap space. So I can still see that object. I can still refer to it, and I can access its state variables. And then the whole program dies at the end again. All right, so that's the end of lecture, and still 4 minutes over. And it's still a lot of content, and I still have to go too fast, even with going over a little bit. I guess if I didn't stop to harass chat a few times, I guess maybe I could have fit that in. But I also want to stop and look at chat every once in a while, because it gives you at least a little bit of time to breathe and digest. It gives me time to breathe too. Heap space 9. Is anyone else lost? And I keep seeing these in chat. If you're lost, come to my office hours. Come to the TA's office hours. Chat with us. Like, I'd be happy to sit down in office hours and go at a much slower pace and explain things to you. Don't just complain in chat. It's not helping anybody. And I do have my office hours. I didn't announce it in class, but it's Thursdays 7 to 8:30 p.m. if I'm not mistaken. But double check the schedule. I'm pretty sure that's what it is. Thanks for featuring me in today's lecture. Byte 1223. Yeah, a lot of bytes and bits today. So do we need to code and whether to use... No, Scala decides automatically whether to use stack or heap. If you're using one of these primitive values, if you're using one of these types in your program, Scala will put it on the stack, and it's going to behave like something that's on the stack. And with my note here that this isn't, this might be different depending on JVM versions according to compiler versions and stuff. Even though some things might be different, the behavior is going to be the same. We're always going to get the same behavior. So these values will always behave as though they are on the stack. And everything else is going to behave like they're on in heap memory. And the most important thing to know there is references. When you have something that's in heap space, you only have a reference to the location of where it lives on the heap. That is the most important takeaway from all of this memory stuff. In labs, I will ask you to draw memory diagrams. The questions in the lab for this learning objective, which will be next week, will ask you questions like, here's a program. Talk to me about what happens in the stack and heap as this program executes. Go line by line like I'm doing in these examples and like I'll do in the examples Wednesday. And just tell me what happens on the stack, what happens in the heap. So you have to know for that, of course. But your takeaway, even after this course, is going to be when I have an object, it's stored in the heap. So it's always passed by reference. I never actually have a variable that stores an object. I have a variable that stores a reference to an object in the heap. And the implications of that, if you don't understand the implications of that in your code, then you're going to get in big trouble. You're going to write broken code a lot, very often. But you never have to tell Scala where to put something. If you have one of these, stack, everything else heap. List, array, map, any physics vector, any class that you write, any type that you create, everything else is heap. Yeah, and don't worry, I mean, if you understood everything that just happened at a deep level and you're like, wow, I get stack and heap now, I would be 1000% impressed. Like, you shouldn't just watch that lecture and be like, I get it. And that's where the 7 hours outside of lecture time starts to come in. Of course, doing lecture questions and doing homeworks. But you should review the lecture. If you could absorb all of that at a meaningful level that fast in 50 minutes, yeah, you're a superstar. You shouldn't really fully understand that. It takes time to digest. Is it in person? P, what are you... this course is fully remote, if that's what you're asking. Professor, this is too hard. Again, complaining in chat doesn't really help. I'd be willing to guess that as you were typing that, you missed something else. Are you going to talk more about stack and heap later on Wednesday? Yeah, so Wednesday is just this is just an introduction to stack and heap. Wednesday and Friday are all about reinforcing stack and heap and talking about the implications. Okay, great. Stack and heap are things, and this is how memory is. Wednesday and Friday are, what are the implications of that? Why should I care? How does this affect the programs I write? And Friday's lecture specifically is just examples. I'm going to go to IntelliJ, spend the whole lecture in IntelliJ, and just play around. I'm going to start playing around with the debugger, which will actually go through your code line by line and show the state of the stack and heap and all the stack frames. It'll give you all that information while your program runs. And I'm going to emphasize that throughout the semester, whenever your code's, and especially in office hours. When your code's broken, run the debugger, look at what's stored in memory and what all the values are of the variables that you're creating. And it can really help you find the issues, the bugs that you've written. Just 1.5 hours per week? You better be spending more than that. Those of you who are lost, I have one question for you. We're starting week 3. Did you put more than 24 hours into this course so far? I expect 12 hours a week at a minimum. If you're under 24 hours right now, you haven't done your part in learning this either. Like, you have to do your part, or of course it won't make sense. It shouldn't make sense if you spent less time than that. Jesse, do you know why I would be getting useless output from my vectors? If you're printing them to the screen, do you have a toString method? Which isn't something we formally talk about until next week, but I flashed it real quick last time. And if you take the physics vector from the physics engine homework, I do have a toString method there for you, which will print out the x, y, and z in a more meaningful way. I assume that's what you mean by that. But if you just print a vector to the screen, it's going to say something like physics vector at some number. That at some number is what I'm talking about with the heap. It's just giving you some number that somehow represents where it is in memory. It's a very loose connection. It's the way the JVM represents it. And the type of that object, which is useless information for you. But if you give it a toString, it can print XYZ for you. I will be there 100,000%. I hope that's why I was talking about office hours. Please visit me in office hours. If you're lost, confused, check out the TAs, of course, because with me you have to wait till Thursday evening each week. Check out the TAs. They're more than happy and qualified to help you out. Especially understanding the concepts. If you come to office hours with conceptual questions, we can help you a lot more than if you just pull up your code and say, this is broken and I don't know why. If you didn't understand lecture and you're just diving into the lecture question, you will have those questions like, this doesn't work and I don't know. But if you have questions about lecture, if you pull up the slides and ask a question, those are my favorite questions. I can actually teach you. When you just pull up broken code and say, fix it for me, it's tougher to really help you because I really have to get down to the core misunderstanding. It's a lot tougher. But if you're like, when you went over this stack example, I just didn't know what was going on. I'd be more than happy to go through that again, slower, 10 times, whatever. Well, maybe not that many if there's a line for office hours. I want to help everybody, but you get the idea. I can help you a lot in office hours. And the TAs can as well. And you should have all been contacted by a TA as well in offering to schedule some time, extra time with you. Please take advantage of that. Talk to them and any concerns you have, get working at it. If you're lost in today's lecture and you don't do anything until next on Wednesday's lecture, in between those two lectures, you don't do anything CSE 116 related, you're still going to be lost. We're here to help you, and obviously study on your own, and then come to us when you just hit a brick wall. We'd be happy to help you out. I just don't like that defeatist attitude, like, this is too hard. I can't do this. No, none of that. Just work at it. You'll get there. It's work. It's tough. Don't get me wrong, but you got to at least put your best foot forward. Yeah, Lipso. So a few times during that lecture, I was regretting looking at chat, but it calmed down a little bit at the end there. Andrew Paul, I'll see you there. Oh, thanks. Thanks, Slidify? I'm pretty far behind live. Let me try to get through these. How do I call to list using this? Like the LQS. Not quite sure what you mean. Do you mean Friday's lecture question? I think you might mean Fridays. We don't have lists today. So this is going to, when you're inside a method call, the keyword this is going to allow you to access the state variables of the object from which that method was called. So somewhere in your tests, you're going to create a vector, and you're going to say vector that I created dot multiply by constant. Inside that method call, this is going to be a reference to whatever vector you said dot multiply by constant on. You're going to have that reference. So this stores the location in memory of the object where you said dot method name. Which hopefully makes a little more sense now that we've seen the heap, at least quickly. You honestly don't need this for the LQ. Yeah, I said that at the top of lecture. Today's lecture, you didn't need for today's lecture question. Arguably, you don't need any of this week to do the lecture questions. But if you don't understand this week, one, you're going to fail the lab next week, and you're not going to get the learning objective complete. But also, it's going to be just more difficult to write your code. I know coding got a lot easier once I started understanding stack and heap and really what's going on in memory. If you don't have a good grasp on that, and you're just really guessing at how objects behave, it just gets a lot tougher. And how scope behaves. I'm going to get a tattoo of 116. Nice. It's like having your ex's tattoo. The heap can be accessed in any order. It doesn't, like, the stack has structure. The heap is just, it's wide open. Do whatever you want out there. I mean, within reason, I guess. But it really feels like when you're coding, it'll feel like you can do whatever you want with the heap. Allocate, whenever you say new something, you're asking the operating system for more memory on the heap, and you don't really care where it is or what. You just get, you just get a reference to that memory location, and that's all you have to care about. So anything that has multiple values associated with it, not even necessarily that goes on the heap, I assume. It's like our example here. This just had one value, but it was still a class that we defined, and it's not one of those primitives, so it still goes on the heap. Even though its one variable is an int, which would normally go on the stack, since it's contained within a type that we created, it's going to be on the heap and passed by reference. Where it need to be first in, last out. That was, the stack needs to be first in, last out. No profanity? Who swore? Did I swear? I might have. Are we going to learn grass and trees? Yes. In linked lists. If you finish rhyming dictionary, so the homework verification lab will be in 2 weeks from now, and you will have a, just like last week you had a TA reach out to schedule an interview, you'll have a TA reach out for an interview for those assignments. But you do have to wait until that week's lab before you schedule that. Once you get, hey, a TA will email you, hey, homework 1 verification interview, let's schedule this. For those of you who do the homeworks early, please review the homework before that interview. I've had students do very poorly on the homework verification, and their excuse was, well, I did the assignment right when it came out, and then I forgot what I did. So just make sure you're looking over your code, remembering what you did and stuff like that. Just a small pointer, so you don't have to do a makeup interview. I was not exaggerating when I said that many hours. No matter what I say, no one will believe me there. I keep saying, I know you don't believe me, but this is true. I know it wasn't true in other courses. It doesn't matter what I say. It's and then, yeah, prime factors. That and I do look at prime factors. That lecture question is like the start of the course. That's when stuff gets real.